Okay, first things first, just to clear up some things, this is going to be shorter than my other videos. So for number 36, we've had a lot of questions on that. Whenever they ask you the rate of disappearance, you can use this equation right here. And remember, it's negative if it's a reactant, and it will be positive if it's a product. And remember, the coefficient of whatever your reactant or product is goes at the bottom. That's your coefficient. So if the coefficient 2, it would be negative 1/2. The change in concentration divided by the change in time. So that is what the rate of disappearance is. So when you're setting these two equal to each other, using those coefficients, you don't have to multiply your end result answer by the coefficient because it's already been taken care of in your relationship right here. So that was the first thing. Kyla had a question if we had to multiply that 0.4 by 2. And we don't, because we've already we already took care of it when we wrote our rate reaction. And remember, rate is the change in the amount of reactants or products divided by the change in time. All right, now 50. 50, I have no idea what I did on my paper. And I can look at my paper and remember, oh, I did this. I couldn't figure out, to save the life of me, what I did. I think I made this problem 10 times harder than what it actually should have been. So when I went back and looked at it, I can condense a whole piece of paper into one little thing. First things first, this is what they gave you in the problem. They gave you time, and they gave you the concentration of sucrose. I did these myself. I did the natural log of this concentration, and then I did 1 over the concentration to get these other values. Now, if you have a graphing calculator, you can just plug these in, bam, get the linear regression, graph it, and you can see which one is the winner. Linear is the winner. If not, all you have to do is look at this. What's the change in between here? Here to here is like 0.042. Here to here is 0.036. And you can keep on going down the line, and knowing that these are not the same differences tells you that it's not linear. So you know it's not going to be 0 order. Same with these guys. If you go down this one, I think this one's, the difference is 0.49, and then this difference is 0.85. Not going to be linear if the differences are not the same. If you look at this middle one, the difference is like 0.42 or something, 0.142, and then like 0.140 or 0.141. Well, those are like almost identical. So that's going to be your answer. That's going to be your linear one, and that's going to be telling you that it's first order. If this one was your linear one, it would be 0 order, and if this one was your linear one, it would be second order. But since this one has the same change going down it throughout, that tells you that it's going to be linear if you were to graph it, and it tells you that it's first order because it's the natural log of the concentration, that it's linear versus time. So it's first order. That's the first thing to do. All right, B, I like graphing, but you don't have to. You can just look at the changes if you want to, once you have all these values. And like I said, you had to calculate these on your own. They were not given to you. You had to actually calculate these. So now for part B, what are the units of the rate constant? So I used an equation that you probably never saw before. So I'm going to use the equation that we're very familiar with. So the natural log, and I'm going to abbreviate sucrose, SUC. And this is initially equals negative KT. Okay, so I'm just going to rearrange this equation to get K by itself. And this is first order, so that's why I used this equation right here. It's first order, that's why I used this equation right here. So I know that the natural log of the concentration of sucrose at one particular time minus the natural log of sucrose initially at 0 divided by T equals negative K. Does it matter what concentrations you put here? No, I just figured it out for all of them, and it does not matter. So if you want, I did it for 0 to 210, but you don't have to. You can do it between 0 and 39 and use these concentrations, or 39 and 80. It does not matter. So I'm going to do the natural log of sucrose at 210 seconds is, I should put this in here for you so you know where I'm getting these, minus the natural log of sucrose initially, which is 0.316, divided by the difference, since I'm using the concentration at 0 and the concentration at 210, my difference is 210 minutes, and that equals negative K. So once you figure all of this out, so once you finish all these, figure out all these, I have these values here. I have them right here, but I didn't want to plug them in and confuse you. So I'm just putting in my initial values. So when I work all this out, my K comes out to be 0.00368 1 over a minute. These are molarities. They're going to cancel each other. Molarity times molarity. They're going to be 0. So you're just going to be left with 1 over a minute. This is so much easier for you guys to understand than what I did earlier, and I apologize. So hopefully this makes sense now. So C, what is the average value of the rate constant calculated from the 3 data sets? Oh, wait. No, this is combining my problems now. Using this rate constant, calculate the concentration of sucrose at 39, 80, 140, and 210 if the initial concentration was 0.316. Now, this is a long problem. Easy problem, but long problem. Now, they tell you in this part C that it is 0 order. And that is the tricky part of the problem, because that changes your rate law expression. Your 0 order is the concentration at a particular time equals negative KT plus the concentration initially. So it's a lot different, a lot easier to use. So they just want you to figure this new concentration out at 39, 80, 140, and 210. So I'll do the first one for you. You have your K, negative times 0.00368 1 over a minute. The first minute they had is 39 minutes. You'd have to do this each time for 39, 80, 140, and 210. That's what's given to you in the problem. They tell you that your initial concentration of sucrose is 0.316 molar. Notice you don't have to do the logs or anything. So if you do this one comes out to 0.172 molar. And I'm just going to write the other ones down here. You do the same thing for 80 minutes. Same thing, except 39, you do 80 minutes, and it's 0.02 molar. 140 minutes. 140 minutes is negative 0.202 molar. So obviously that can't exist. You can't have a negative concentration. So that would be 0 molar. Well, if you have no sucrose left at 140 minutes, that's what that means. You don't even have to figure it out at 210 minutes, because if you have none left at 140 minutes, you have none left at 210 minutes. And that is the problem. A lot easier. Earlier, I think I even calculated how much time it actually took to get rid of all the sucrose. And you don't even have to do that. That's what I did this. You weren't even asked that. That was rearranging the equation. Using your initial concentration and also putting in your negative K value. So if you look at this, you knew that that time that all of that sucrose would have been used up is 85.9 minutes. But they didn't ask you to calculate it. So like I said, when I did this problem earlier in the day, I made it so much harder than it was. I apologize. All right, so I hope that helps everybody. If you have any equations about or questions about the lab, some people had, you can stay on. If you're done, you can just get off. The part 2 challenge, a lot of people are having questions on number 1. So for those part 2 challenge number 1, for A, B, and C, you don't have to include the potassium ferricyanide, the diphenylamine, or the sulfuric acid, because they say they're always present in the flask. They want you to indicate which compounds are present during these 3 points. Well, before the titration, obviously you have no zinc sulfate because you haven't started titrating yet. Okay, so the only thing you have present then is your potassium ferrocyanide. Right before the end point, well, before the end point is happening, all the zinc sulfate that you're adding, that's being reacted. So you don't have any extras before the end point. So again, that's leaving you only with potassium ferrocyanide. It's only after the end point do you have any zinc sulfate left. Number 2, the proposed mechanisms. You just have to watch the color changes. It says record what you would observe for each test if the mechanism was resulted in the color change. So you know what color everything is. It says the free DBA is blue. So what would be happening if you're titrating? If you started with blue, it would go to colorless. Is that what you saw? I mean, this is very easy. Don't make that number too hard. I can't tell you all the answers, but it's not difficult. So the additives is what you added. Really easy. And the predicted observation is from what color to what color for each of them. Okay? They might be the same, they might be different. I hope that helps you. All right, thanks.